So today's lesson is going to be on the fundamental theorem of calculus. We've already talked about a lot of these ideas. For the first half of the course, we've been pretty much dealing with differentiation, which is referring to the slope of the tangent line to the curve at a given point, and then exploring ideas behind that. Now we're moving on to integration. We've already talked about the antiderivative, which is just the reverse process of a derivative. And now we're going to talk about a definite integration, which is referring to the area under the curve. So now I'm actually going to teach you how to find the definite integral algebraically. Okay, so again, anti-differentiation is just the reverse process of a derivative, and definite integration is just the concept of area under the curve. So this refers to area under curve, and this refers to reverse process of derivatives. Now the first theorem we're going to cover is the fundamental theorem of calculus. This is the first time I'm actually going to show you how to find the area under the curve without using an approximation method or simple shapes. Okay, so when we go through the example, you're literally going to take little f of x, which is your function. You're going to take the antiderivative of the function, which is capital F of x. You sub in the top value, which is b, into that antiderivative, subtract off, sub in the bottom value into that antiderivative, and then you just work out the value that's going to be the answer. This answer is going to be a number which represents the area under the curve, as if we were going to do the simple shapes or an approximation method. Okay, so let's actually go through and find the value of this definite integral. So here is my function, little f of x. I need to do the antiderivative of this function. So this is just the reverse of power rule. I add 1 to the exponent, divide by what I added, minus the antiderivative of 3 is 3x. Now the big difference here is we don't add a plus c. We just put a line indicating that we're going to be subbing in the top value and the bottom value. So 2 cubed over 3 minus 3 times 2. That's me subbing in the upper value. This is like the f of b in the theorem. Minus, I sub in the lower value, 1 cubed over 3 minus 3 times 1. And this is like my f of a, the antiderivative with a subbed in. Then we just work out this value. And when I work out this value, I'll just use my calculator really quickly because obviously I can't do simple math. So 2 to the power of 3, divide by 3, minus 6, minus 1 over 3, minus 3, and this looks like when you work it out you'll get a negative 2 over 3. Now because this answer is negative, if I were to draw the value of the area under the curve, I would draw the function x squared minus 3, which is a parabola opening up, move down 3 units, and I'm evaluating that integral from x equals 1 to the value 2, which is, say, here. So the reason my answer is negative is because there's more area below the curve than there is above the curve. So negative because more area below the curve than above it. Okay, let's look at the next example. I'll pull it over here. So we want to do the integral of absolute or square root of x. This would be 3x to the 1/2, rewriting the function. I would do the antiderivative, which means I add 1 to the exponent, which will give me 3 over 2. So this will get multiplied by 2 over 3 x to the 3 over 2. And I want to evaluate that from the values 1 to 4. Okay, so the 3's cancel. This would be 2, 4 to the 3 over 2 minus 2 times 1 to the power of 3 over 2. And again, my 3's have canceled out here. And then you just work out this final answer. So on the AP exam, you don't have to actually work it out, but you can just work out that answer as a value. Okay, let's try the last example. So we're doing sec squared of x. So what function gives you a derivative of sec squared is tan. So my antiderivative is tan x. We evaluate that from 0 to pi over 4. So I'm getting tan of pi over 4 minus tan of 0. Tan of pi over 4 is 1. Tan of 0 is 0. So this just works out to an area under the curve of 1. Okay, so this is the first time I've actually shown you guys how to actually do the definite integral without approximating or doing simple shapes. Now, when you have an example that has an absolute value, you have to remember that the absolute value is kind of like two functions. So what we need to do is we kind of need to use the property of integrals to break up those two functions so that I have two separate areas. So the value of absolute value of 2x minus 1 that makes that inside part 0 is x equals 1/2. So that's sort of my starting point on the x-axis where it's kind of like my mini vertex. So there's a point here. And then I know my graph is going to go like this in its V shape from that kind of vertex point. Now I'm interested in finding the area under the curve from the value x is equal to 0 all the way to x is equal to 2. So that's literally two triangles, but now instead of doing them using triangles, we're going to do them using the fundamental theorem of calculus. So we use the properties. We are going to go from 0 to 1/2 of my function plus the integral from 1/2 to 2 of that same function. And now, literally, because the absolute value sort of represents two functions, it represents 2x minus 1 when x is bigger than 1/2, which is this side, and it represents minus 2x plus 1 on the other side when x is less than 1/2. So now I can literally sub those functions in. You're going to get negative 2x minus 1 dx from 0 to 1/2 because you have the negative of that function, plus the integral from 1/2 to 2 of the positive version of that function. Now, if this were an AP question, you may be able to use your calculator to work that out, but again, I would expect you to do this by hand. So this is equal to the antiderivative of negative 2x would be negative x squared. The antiderivative of positive 1 would be positive x. I use a line to indicate I'm subbing in the top limit and the bottom limit. So that's that. Plus, I do the integral of the second part, x squared plus, minus x. And I'm evaluating that from 1/2 to 2. And then we just literally sub the values in. So I'm going to sub the values in and let you work out the final answer. So minus 2 squared plus 2. Oh, whoops, I'm making a mistake. So we have to start with the first integral function. So it's going to be minus 1/2 squared plus 1/2 minus, sub in the lower limit, minus 0 squared plus 0. Now I'm going to add that on to subbing in from the bottom part, which is 2 squared minus 2 minus 1/2 squared minus 1/2. And then you literally work that value out, and then that would be your final answer. And I will let you just work this value out. Otherwise, this video recording will last forever. Okay, now again, we're going to start doing areas under the curve visually. It's the same thing what we're doing. Find the area of the region bounded by the graph of this function, a parabola. Okay, bounded by the x-axis, which is this line right here. Oh, that's the y-axis. So that's the line x equals 0. The x-axis, which is my x line here. X equals 2, which is this line right here. And I'm literally looking at the graph and this area in pink. So in order for me to set this area up, we've done this before with the simple shapes. We're going to go from 0 to 2, which are our lower bound and our upper bound on the x-axis. We take our upper function, 2x squared minus 3x plus 2, and we're integrating that with respect to x, right? So we're doing the same thing as what we would have done with the approximation methods, but now we have an actual strategy on how to solve this integral. So I'm going to find the value of the antiderivative, which is 2 over 3x cubed minus 3 over 2x squared plus 2x. We showed that we're going to evaluate it from 0 to 2. So 2/3 2 cubed minus 3 over 2 times 2 squared plus 2 times 2. That's my upper limit. I'm going to work out that value minus, when I sub 0, I'm going to get 2/3 0 cubed, which is 0, minus 3 over 2 0 squared, which is 0, plus or minus 0, plus 0. So it's literally the value of what I'm getting right here, which again, you can work out on a calculator and write that value down. That will represent the area in here in pink. Okay, we should expect a positive number because that area sits above the x-axis. Okay, mean value theorem for integrals. This is pretty much very similar to the mean value theorem in general, but now instead of talking about a function where we're doing so for the function, our mean value theorem was f prime at c for some value of c is given by f of b minus f of a over b minus a, and then there were some conditions here which I don't remember at the moment. I think it was continuity of the function, so and differentiability. So this tells us that the slope of the tangent line is equal to the slope of the secant line for some value c in that interval a to b. Now the mean value theorem for integrals is quite different. It actually gives you the height of the rectangle that you needed so that the area under the curve is actually equal to the value of the integral. So the c value that they show here represents some height of the function c. Well, this would be f of c, which would represent the height of that function. So this area of this rectangle would actually be equal to the area under the curve, which is represented by, well, let me draw this function again. So if I were to draw this function again like this and do the area under pink like they have for us here, the c value actually makes it so that this area in pink is equal to the area of that rectangle. Area in pink equal to area of rectangle. Okay, so that c value is somewhere in there and it will give us a height. You can find a c value that will give you a height f of c that will be equal to the area under the curve. This is actually quite powerful because area of an rectangle is much easier to find than an area of a function that is all curved and we can't actually approximate it. Okay, now if I isolate for f of c in this formula, this is actually called the average value of a function. So the average value is f of c, which is representing this height of this rectangle produced to make sure that that area of that rectangle is identical to the pink area. So I would have to divide by this b minus a on both sides. And because the b minus a is only a number, it doesn't even have to actually matter, and it can come outside the integral. So this formula represents the average value of a function, okay? So when you see average value, we're thinking height of some rectangle that gives the exact rectangle needed to the height of some rectangle that gives the exact rectangle needed to make the area of the function actually equal. So again, that pink area equals the rectangle. So here's my rectangle. That height of this rectangle is f of c. We would still multiply by b minus a, which is my height, or my base of the rectangle. And then the actual area under the curve would be this. And this rectangle and that area are the same. Okay, sorry, my sentence doesn't seem to be great there, but hopefully you understand what I'm talking about. Okay, this is a key idea. Okay, the height of the rectangle, whatever rectangle that is f of c, the height, and that area of that rectangle formed is exactly the same of the area under the function, that pink area. Okay, so let's actually do an example. It says find the average value of the function on the interval. So I'm going to do 1 over b minus a, the integral from 1 to 4 of f of x dx, and you can sub your function in. My a is represented here, my b is represented here, and there's my f of x. So I just sub in the values. 1 over 4 minus 1 is 3, integral from 1 to 4, f of x is 3x squared minus 2x dx. We're actually finding the height of that rectangle. This is like f of c, if you wish. Okay, so we'll work out this value, 1/3. Okay, the integral of 3x squared is x cubed minus x squared. Those numbers in front will cancel out. We evaluate from 1 to 4. So I'm going to leave the 1/3 on the outside. I'm going to work out the value of 4 cubed minus 4 squared, 4 to the power of 3 minus 4 squared, which is 48, minus 1 cubed minus 1, which is 0, and that 1/3 is on the outside of all of it. So 1/3 of 48 is 16. So that area, the height of the rectangle needs to be 16, so that if I were to do f at c, which is equal to f of c times b minus a, that would be the rectangle. And I'm making it equal to 0, whoops, not 0, 1 to 4 of f of x dx. So this is area under curve, and this is area of rectangle. So we're finding that rectangle that makes these areas the same. So this is the average value of the function.